Today we're going to take a look at confidence intervals, which is an example of inferential statistics. So far in this class, we've done a lot of descriptive statistics, finding means and medians and standard deviations, basically describing sample and population statistics and parameters. Now in inferential statistics, what we're going to do is use sample information to predict population information. So suppose we have a population and we are interested in finding the mean mu. So our population mean is unknown. And maybe we know the standard deviation for the population, sigma, or maybe we don't know it. And we'll take a look at those two cases in just a little bit. Okay. But the way we're going to predict or estimate what mu is, because that's our goal here, is to find an estimation for the population mean mu. And the way we're going to do that is by taking a random sample. So here's our sample. And we can compute its mean, x bar. Now this sample mean in itself is an estimation. This is what's called a point estimate. And it might be close to the population mean, but it's probably not going to be exactly the population mean. Each sample is going to have its own sample mean. Now if I were to just draw a picture of this, so let's assume this is our original distribution. Right? And maybe it's normal, maybe it's not, but say this is what our distribution looks like, and of course we have our mean mu in the middle. And when we go and take a sample and compute the sample mean x bar, maybe this particular sample mean lands over here. Maybe it's close to the population mean, but not exactly the same as the population mean. And well, this is a point estimate, which is an okay estimate, but a better estimate would be to make an actual range of values around x bar, that hopefully this range of values does contain the actual population mean. And to compute this range of values, we're going to do x bar plus some margin of error, which we'll call E. And then we can also compute x bar minus this margin of error, E. And when we do this, when we create this range of values, this is what is called a confidence interval for our population mean mu. So that's all it is. It's a range of values that hopefully contains the population mean mu. Now, to make this range of values, well, we have to define E. So let's take a look at our margin of error. So our formula for the margin of error, E, is going to be, we're going to take what's called a critical value. And a critical value, it's basically just a z-score. And we're going to see in just a minute how to find these critical values. Okay. And the critical value is going to depend on our level of confidence. Okay. And by level of confidence, basically we mean how confident are we that this range that we create, or this confidence interval, really does contain the population mean. So we take our critical value and we multiply by sigma, the population standard deviation, divided by the square root of n, where n here is our sample size. Now notice in this formula, we're using our population standard deviation. So this is assuming we know our population standard deviation. So this is our first case where sigma is known. And in this case, we get to use our margin of error formula that we came up with. E is equal to the critical value times sigma over the square root of n. Now, in general, if our population mean mu is unknown, then it's very likely that the standard deviation is also unknown. And in this case, since we don't know what sigma is, instead we have to use our sample standard deviation, which remember we call that S. Okay. And we also have to use what's called the student's t-distribution, which we are actually going to take a look at in the next video. For today, in this video, we are going to be working with the case where sigma is known. All right. Well, now, going back to our margin of error and finding these critical values, to find these critical values, these are basically listed on your standard normal table. So the table we've been working with for the last few weeks. If you look at the bottom, you're going to see a whole list of different confidence levels and then their associated critical values. And I'm going to write down just kind of the most commonly used ones. So if we want a confidence level of 90%, or we want to be 90% confident that the population mean mu does land within this range that we create, well then the critical value that we would use is 1.645. If we want to be 95% confident that our interval contains mu, well then we have to use a larger critical value of 1.96. And if we want to be 99% sure that our interval contains mu, then we would use a critical value of 2.58. Okay. And certainly there's more confidence levels, and those are all listed in your book, in your table. By the way, the standard normal table, I realize, is also in the very inside cover of your book. If you just open your book to the inside cover, there it is. All right, let's take a look at an example. So here's our example. Let's suppose that the weights of hummingbirds in a region are normally distributed with a standard deviation of 0.4 grams. So notice we're given the population standard deviation, okay? But we are not given the population mean. Our goal is to construct a 90% confidence interval for this population mean. And in order to do that, we're given this other information. We're given that a sample of 16 hummingbirds have a mean weight of 3.2 grams. Okay. So let's find this 90% confidence interval. We're going to do this in two steps. First, let's find our margin of error, E. And so remember, our formula here is we take the critical value times sigma over the square root of n. Okay. So our critical value, which is going to be the one that corresponds to a 90% confidence interval, right? So let's come back here. For a 90% confidence level, we want to use a critical value of 1.645. So 1.645. And then we have to multiply that by sigma, which we're told is 0.4 grams, divided by the square root of n. And what is n in this case? Oh, n is our sample size of 16. So down here we'll have the square root of 16. And if we do this computation, this is 1.645 times 0.4 divided by square root of 16 is 4. You could plug this into a calculator, and what you would get is 0.1645. By the way, our units here would be grams, right? Same as the units that are given to us in the problem. And now we're ready to construct our confidence interval. So to find the kind of lower end of our confidence interval, we're going to take the sample mean x bar, and we're going to subtract our margin of error. So we would get 3.2, that's our sample mean, minus E, which is 0.1645. And this comes out to 3.0355 grams. So that's the lower end of our confidence interval. The upper end of our confidence interval, we're going to take our sample mean x bar and we're going to add the margin of error E. So 3.2 plus 0.1645, and this comes out to, what is this, 3.3645 grams. Cool, so our confidence interval is the range of values 3.0355 grams to 3.3645 grams. And we are 90% sure, or 90% confident, that this interval really does contain our population mean. Okay. Now, to say we're 90% confident, what does that mean exactly? What this means is that there is a 90% probability that this interval really does contain the population mean, mu. Now, one more thing to note about this. Notice in this example, our distribution of hummingbird weights are normal. The distribution is normal. And what if our distribution is not normal? Well, let's take a look at this note I have on the next page. In order to use this method that we just came up with of finding our confidence level or confidence interval, it's appropriate to use this method if either the distribution of x values is normal, like in the example we just did, and in this case, any sample size will work. In our example, we had a sample size of 16, but in general, any sample size will work. Okay. Now, what if our distribution is not normal? What if it's skewed left or skewed right or maybe bimodal? Well, in that case, we need to make sure that our sample size is at least 30 and should be greater than or equal to 30. And there we go.